Hello everybody and welcome to today's lecture. So today we're going to start talking about chapter 2. We finished up chapter 1 in the last video, which was dealing with arithmetic. So make sure you're comfortable with those before moving on with this video. In this video we're going to start talking about algebra. Okay, the very basics of algebra. This will be a lot of definitions at first. So what exactly do we mean by things like variables? How do we translate the language of algebra? So we're going to start looking at some examples like that. This is section 2.1 in the book. So let's get started with a couple of definitions here. Just for what algebra is, there's a lot of different ways we can define it. I guess a good way to think about it is the branch of math dealing with finding some kind of unknown. Okay, at least for us. Or just dealing with unknowns in general. So, as an example of something, we'll solve later, if we have an equation, which we'll define later, like x plus 3 equals 5, how do we know what the letter x is representing? What number is that representing? Okay. So this is like a very basic version of algebra. Algebra is a very big branch of math that encompasses a lot of things, but the kind of algebra we're going to be looking at is mostly just figuring out unknowns, or like solving equations, or modeling real world situations using what we're going to call a variable. Okay. So let's go ahead and get started with some definitions here. Okay. So the first one, a variable. A variable is a quantity that is unknown. Sorry, I know I write my K's weird. I'm trying to stop. That is unknown and or changes. Okay. So it's a quantity that is either unknown or it changes or both. Okay. So we usually use letters to represent variables. Okay. i.e. x, y, a, n, etc. Okay. Or we might even use some Greek letters. We probably won't in this class, but in like trigonometry or geometry, when you're dealing with shapes, a lot of the time they'll use Greek letters like alpha, beta, gamma, theta, etc. Okay, so we probably won't use any Greek letters, but like I said, in other branches of math, they typically will. In statistics, you typically use Greek letters a lot. In physics, you use Greek letters a lot. So you might see them in the same context. Okay. So in the one that we were just looking at, like x plus 3 equals 5, x here is an unknown. It's not a value that changes because there's only one value it can possibly be for this equation to be true, right? X has to be 2 here because 2 is the only thing you can add to 3 in order to get 5. So in this case, it fits our definition still because it's an unknown. The way we write it initially, we have to figure out what it is. In other contexts, maybe like y equals 2 times x. So this is y equals 2 multiplied by x. Here, x and y are both variables. They're unknown, but they also can change because if x is one thing, y is going to be a different thing. For example, if x is 1, then y is going to be 2 times 1, which is 2. If x is 0, y would also be 0. If x is 2, y would be 4. Okay. So they are both unknown and they change. Okay. And in the first example, it doesn't change, but it's still unknown. The opposite of a variable is what we would call a constant. Okay. A constant is a quantity that does not change. Okay. Um, the way we're going to look at constants right now, we always will know them. Eventually, if you were to go on in math, you'd maybe tweak these definitions a little bit because there could be constants that you don't necessarily know what they are. So you'd probably define variable a little bit differently because of that. But in our case, a constant is going to be pretty much always a known quantity. Okay. So an example of this would be something like 3, right? The number 3. 3 is always representing 3 of something. It's never representing 4 or 5 or anything. 3 is always 3. Okay. So just any number basically, right? 0. You could have 1/4. You could have -2. We'll talk about negatives and fractions later, but these are all examples of constants. There's some other constants that we use letters for, even though we do know what they are. For example, pi, right? Pi is the value that's approximately 3.14 if we use it in decimals. But it's really more than that. It's really an infinite decimal, and we can't actually ever write it down because it goes on forever. So we just use the letter pi to represent it instead. There's some other numbers like that, like e, which we're not going to talk about in this class, but you might see in the next class, Math 101, which is similar to pi. It's just 2.7, I think it's 2.78. There's some other things like the square root of 2. We'll talk about square roots later, but this is essentially asking what number times itself gives you 2. And there's not a nice answer for this. It's an infinite decimal also, so oftentimes we would just leave it as the square root of 2. So this is a constant because it's one value. It's just hard to actually write down what that value is, so this is the way we represent it. Okay. And sometimes if we don't know what the quantity is, but we do know that it's constant, we know that it's one number, oftentimes we'll use like the letter C to represent that. But we're not going to use that in that context in this class, which is why on the variable side, I have that it is unknown. So like I said, later in other math classes, you might not consider unknowns to always be variables, because sometimes you know that something is a constant, it doesn't change. You just don't know exactly what it is, or maybe you just don't care exactly what it is because it doesn't make a difference. So for our purposes, a variable is going to be something that changes and something we don't know. A constant is going to be something that doesn't change that we do know, like just a number basically. All right, so let's talk about I'm not going through every single thing in the book, so I'm just gonna kind of skip around here. So this one's probably something you've seen before. The equal sign. Okay, this isn't really a definition. Maybe this is more like notation. So the equal sign, which looks like this, which we've used before in the first chapter. But what this really means is that two things have the exact same quantity. So this signifies that two quantities are exactly the same. Okay. So if I write 2 equals 2, this is signifying that 2 and 2 are the same number, right? They're both representing 2 of something, which we know to be true. If I write x equals 2, this is telling us that the letter x is representing the quantity of 2. Okay, it's only going to represent 2. It can't represent 3, 4, anything. It's saying it is 2. If I write x equals y, okay, then we don't know what either of these quantities are, but what we do know is that whatever x is, y is the same thing. Okay. So with stuff like x plus 3 equals 5, we can use this to our advantage because we know that whatever x plus 3 is, it has to be the same thing as whatever 5 is. So we just have to look for, okay, what number can we make x so that we add 3 to it and we get 5. Okay. And that's how we can figure out that it's supposed to be 2. So there's some other things called inequalities. We're not going to look at these too much, but they're definitely worth mentioning because they'll definitely make appearances. The equal sign relates to things and says that they are equal. Inequalities relates to things without saying that they're equal. So this could be as simple as something as x does not equal 2. So this sign right here means does not equal. So we don't know what x is, but we know that it's not 2. So it's an equal sign with a line through it. We could say 3 does not equal 2. Okay, and we know that's true because 3 doesn't equal 2. They're different numbers. So there's the not equal. Okay, so let's make a little chart here. Some other ones that you might have seen before. We have less than. Get better. Less than. Okay. So 3 is less than 5. So this is relating to quantities by their size. And it's saying that the left one is smaller than the right one. And we read it as 3 is less than 5. Okay. So if we have x is less than 5, well, we don't know what x is, but we know that it's smaller than 5. It could be 4, it could be 0, etc. It can't be 5 because it's strictly less than. We can't have it be equal to. If we want to say less than or equal to, we write the less than sign and then we put a bar underneath it. So this would be less than or equal to. So x is less than or equal to 5 means that x could be 5, it could be 4, it could be 3, etc. We could also say 5 is less than or equal to 5. That's true, right? It's the it satisfies the equal part. It just needs to satisfy one of them. On the other hand, we might want to say greater than, the opposite of less than. Or similarly, greater than or equal to. So we could say x is greater than 5. So x could be 6, 7, 8, 9, etc. X is greater than or equal to 5. So x could be 5, 6, 7, 8, etc. We'll want to look at this when we're talking about fractions, because oftentimes we want to it's not as straightforward to know which fraction is bigger, right? If you're given two numbers, say 17 and 35, and you're asked to place one of these signs in the middle of them, it's usually pretty easy to go, okay, we know 17 is smaller than 35 because we're used to these numbers. We use them a lot. With fractions, it's not necessarily so easy. If we have 13 seventeenths and 12 sixteenths, it's like, I don't know which one is bigger. We would have to do a little bit of work to figure this out, right? It's not so clear whether 13 seventeenths is bigger or 12 sixteenths is bigger. The numerator in the left one is bigger, but the denominator is also bigger. The denominator being bigger makes fractions smaller. So it's not so easy to figure it out. So when we go to the fraction chapter, we're going to want to do problems like this where we figure out which one is bigger. Okay. Okay. So let's talk about another definition here. An expression. Hang on, I think I want to talk about a different thing first here. I think I might go in a little bit of a different order. Oh no, here we go. The book has two different definitions for expression, so I'm going to use their second definition. An expression is a number, variable, or a combination of these with operator symbols. Okay. What do we mean by operator symbols? These are the things we did in chapter 1. Plus, minus, multiply, divide. Okay. So these are addition, subtraction, multiplication, division are what's known as operations. They're not the only four, but they're the most common four. So the operator symbols are the symbols that we use for those, including the other notations like the dot for multiplication or the asterisk or the bar for division. So an expression is just some combination of these. Okay. So some examples, we could have x plus 3. So this is a combination of x and 3 with the addition operator symbol. We could just have the number 5, right? So the first part of the definition says it's a number. So it could just be a number, could just be a variable, maybe y. We could have a lot of different things. We could have x plus 5 times 4 divided by 7. Okay. Minus 2. Like we could just keep going with it. All of these would be expressions. Okay. Related to an expression is an equation. An equation is a statement that two expressions are equal. Okay. So an equation will always have an equal sign. So you can look at the same root of them, right? Equa and equa. Equation means you have an equal sign. So x plus 3 equals 5. We're taking our first two expressions we had here and we're putting an equal sign in between them. So it says this expression is equal to this expression. Okay, it's saying that they're equivalent. A equals B plus C, right? This would be an equation. This isn't necessarily one we can solve, right? Because we can't figure out what A, B, and C are, because, I mean, they could be anything. So equations don't have to be solvable like the first one is, but they can be. The one we looked at earlier, y equals 2x. We don't have to have variables even. We can just have 5 plus 3 equals 8. That's a type of equation, right? 5 plus 3 is an expression, 8 is an expression, and we're saying that they're equal. Okay. All right, let's talk about simplifying expressions. Oftentimes when we're given expressions, they're not necessarily nice expressions. Okay. So what we want to do with them is we want to make them as simple as we possibly can. So we'll talk about simplifying expressions. First, we should define exactly what we mean by the word simplify. Okay. First, let's look at what the word term means in math. Okay, term is a product of numbers and or variables. Okay. A product of number and or variables. So this could be 3 times 5. That would be a term. You could just write it as 15. Right? 15 would be a term. More commonly, we might see something like 3 times x. Okay. So we're multiplying 3 and x together. This is a term. Okay. So the expression (5x plus 7 plus 3y) has 3 terms. Right? You have the 5x part, the 7 part, and the 3y part. So another way we could define an expression is a combination of terms with the operation symbols, specifically with addition and subtraction. Because, see, the multiplication is multiplying two things together makes it one term. So an alternative definition of expression would be a combination of terms using addition and subtraction. Okay. So in general, when we say simplify, usually what we mean is reduce to the smallest number of terms. Okay. So let's think about how we can do this. Well, some examples are easy, right? We already know how to do this from chapter 1. If we have something like 5 plus 3, then we can just simplify this to 8. Okay. In the first expression, we have 2 terms with the 5 plus 3. In the second expression, we have 1 term. We have just 8. What if we have something like 5x plus 3x? Can we do anything with this? Well, let's think about what this means again. So 5 times x, if we think back to multiplication, um, this is like adding x to itself 5 times, right? So that's the 5x part. The second part, the 3x, is like adding x to itself 3 times. So we expanded it, and now if we want to put it back together using multiplication, well, we're adding x to itself 8 times. So this is the same thing as 8x. Okay. So this is maybe what we would expect to get from something like 5x plus 3x. We just get 8x. So at the end, all we did was add the numbers out in front. Okay. And by the way, the numbers out in front, okay, the numbers in front, so the number part of the term, we could say, the numbers in front are called coefficients. Okay. So in this problem, to do the 5x plus 3x, we didn't have to expand it. What we could have just done was added the coefficients, and then the x just comes along for the ride. How do we know we can do that? What if we have 5x plus 3y? Now can we add anything together? Well, let's expand it back out and check. So we're adding x to itself 5 times, and then we're adding y to itself 3 times, right? But now there's nothing we can do, right? We can't put x and y together. We would have to know what, like, there's no way we can use the rules of multiplication like we did for this part because we had all of the same number. Here, we don't know what x is, we don't know what y is, so we don't know what we get if we combine them. Here, even though we know what even though we know what x is, or we don't know what x is, we know that x is the same as x, right? We know that these are all the same number, so we can use the rules of multiplication to put them together. Here, we don't have something like that. So there's really nothing we can do here. So all we would do is just leave it as 5x plus 3y because this is only 2 terms, whereas this is 8 terms. Okay. In this one, we reduced it from 2 terms to 1 term. So what we can do is we can put them together like how we did in this first one when we have what's called like terms. Okay. So like terms are terms with the exact same variable part. Okay. So the variable part has to be exactly the same. And I mean exact. Okay. They both have to be x or they both have to be y. So 5x and 3x are like terms. Okay. So we're able to add them together. 5x squared 3x and 3x are not like terms. Okay. So we'll talk about what square means in 1 second here. That's the next thing we're going to talk about. But this is an exponent, and this means x times x. Since this is x times x, and this is just x, these are going to be different numbers, right? If x is 4, for example, this one is 4. This one is 4 times 4, which is 16. So these are different numbers. Even though they both have x in them, they're still different numbers. So these are not like terms. 5xy, 3x, 4y. These are all different terms. They're not like terms, right? This one has an x and a y. This one has just an x. This one has just a y. If x was, say, 2 and y was 3, then this number's 2, this number's 3, this number is 6, right? The xy part. So they're all different, so we can't put them together. Okay. We can combine like terms by adding or subtracting, whichever one it says to do, their coefficients. Okay. So if I have something like 5xy plus 2x plus 3xy plus 7x, okay, 5xy and 3xy are like terms. So we can put those together by adding the coefficients together, the 5 and the 3. So we get 8xy. Okay. Now 2x and 7x, those are also like terms. So again, we can add their coefficients together, the 2 and the 7, and we'll get 9x. Now we're done because x, y, and x are not the same, so these are not like terms. Okay. So this is how we would combine like terms here. All right, let's talk about exponents now. Okay, I said we would do that next. Exponents. So exponents are shorthand for multiplication in the same way that multiplication is shorthand for addition. Okay. So if we have 5 and we have a 3 written up here as a superscript, that 3 is called the exponent. Okay. Or sometimes it's referred to as a power. The 5 is referred to as the base. Okay. So that 3 is, I said it's shorthand for multiplication in the same way multiplication is shorthand for addition, meaning 5 to the third is telling you take 5 and multiply it by itself 3 times. Okay. Just like 5 times 3 would tell you to do 5 plus 5 plus 5. 5 to the third power, that's how we would read it, is 5 times 5 times 5. Okay, so we end up getting 125 here. So we would read this as 5 to the third power. Okay. Or with 3 in particular, we could read this as 5 cubed. Okay. So the 3 part is sometimes referred to as cubed, and that's because if you had a cube, right, I can try to draw a cube here. Actually, I think I can just put a shape in. Let me do that. I don't think it has 3D shapes, so I'll just draw a cube. Okay, something like this. And we have this side, and this side. So these are all the same. I used the letter L for length. Then length times length times length is your volume, and this is length to the third power. So you get, so the reason we use the word cubed is because it gives us the volume of a cube. Okay. You don't have to know that, but that's just where it comes from. if we have 5 to the second power, this is 5 times 5. It's telling us multiply 5 by itself twice. Okay. So we have, so we get 25. And this could be read as 5 to the second power, just like this is 5 to the third power. Or more commonly, this is read as 5 squared. Okay. Similarly to the cube, if we have a square, and let's just say we have 5 on each side this time instead of like L, then the area of the square is 5 times 5, which is 5 squared, right? So that's why we use the word squares, because it gives us the area of a square. And we use the word cubed for this one because it gives us the volume of a cube. So we need to be careful with the exponents. Oftentimes, when we're first learning about exponents, I see people always tempted to write this as 3 times 2, right? And this is not true. So these are not the same. Okay. 3 squared is 3 times 3, right? You're multiplying by itself. So we end up getting 9 here. So if we have something like 2 times 2 times 2 times 2 times 2 times 2, one way to simplify it might be to write it with exponents, right? It doesn't actually technically decrease the amount of terms, but it is definitely simpler to look at it with exponents. So what we would do is we count the copies, the number of copies we have. We have 1, 2, 3, 4, 5, 6. And we write it as 2 to the 6th power. Okay. So instead of writing out all that multiplication, we can just do it succinctly with exponents instead. And there's a lot of different rules we can do with we can learn about exponents, but those are saved for chapter 10. So we'll come back to these a lot later. The reason we're talking about them now is because we want to talk about order of operations. And we need to talk about exponents first in order to do that. Okay. All right, order of operations. So remember, operations is like the addition, subtraction, multiplication, division. But what if we have a lot of these different combinations of things and we don't know what order to do them in? Okay. For example, the one I wrote up here, where was it? X plus 5 times 4 divided by 7 minus 2. How do we deal with this? What do we do first? Okay. We're going to look at ones without variables. So we won't use that example. But what if we have something simple like 5 times 4 plus 3? Okay. How do we know what to do first? Well, the parentheses they're kind of like a guide. The parentheses are always telling you you should do this first. Okay. That's the whole purpose of parentheses, is to go, okay, look at what's inside of these first and then deal with what's outside. Okay. So we should always do the parentheses first. So in this case, we would do the 5 times 7 because we do the 4 plus 3 that's inside the parentheses. Now we only have one thing to do, which is multiplication, so we get 35. So parentheses should always go first. Okay. Now what if we have 3 times 4 squared? Okay. So we have two things going on here. We have multiplication and we have an exponent. Well, should we do the exponent first or should we do the multiplication first? Well, if we just like think about it, the 4, it's not really a 4, right? It's really whatever it is when it's squared. Whereas the 3, like for example, if we did 3 times 4 first, right, then we get 12, and then we square it, we get 144. This doesn't feel right. The reason it shouldn't feel right is because remember what the exponent is, right? The exponent is multiplying by itself. So it should be 3 times 4 times 4. But that's not what 144 is, right? 3 times 4 times 4, now we just have multiplication, so we can just do it however, whatever order we want. 3 times 4 times 4 would be 12 times 4 is 48. So this isn't correct. Doing the multiplication here didn't lead to the right answer. The reason for that is because if we do 12 squared, well, we know 12 is 3 times 4, right? So this is like doing 3 times 4 3 times 4 times 3 times 4. So we have an extra copy of the 3. That's what the issue is. Okay. So that's not what we want to do. So we need to take care of the exponent first. We either have to evaluate the exponent, or we could just write it out the long way like this. But either way, we got to do the exponent first. Okay. So after parentheses, the next thing should be the exponent. Okay. So after that, we have multiplication, division, addition, and subtraction. The multiplication and division should come first. Okay, this is more of like a convention thing. And then after that, addition and subtraction. Now notice I didn't say multiplication should always come before division, because it's not necessarily the case. Here, let me go. The multiplication and the division, let me write it like this. Okay. These ones should be, all right, I'm trying to make this clear. These ones should go together, and you should just do them left to right. Okay. So you don't always need to do multiplication before you do division. You should just, if you have both of them, you should just approach them left to right. So for example, 10 divided by 10, actually let me say 10 divided by 5 times 2. The convention is to do the 10 divided by 5 first, because all we have left is multiplication and division. So we should just approach them left to right and do whichever one comes first. Okay, so 10 divided by 5 is 2, and then we multiply to get 4. This is different than if we did the multiplication first. 5 times 2 is 10, and then we do 10 divided by 10 is 1. So we do get different answers. So the convention is to do it from left to right. Same with addition and subtraction. You don't do addition before subtraction necessarily. You just do whichever one comes first. So addition and subtraction go together. So the typical way I remember this is I just look at the first letter of each one here and go look at PEMDAS. Okay. So I remember it by the word PEMDAS. A lot of people remember it by the mnemonic device, please excuse my dear Aunt Sally. Okay. So please excuse my dear Aunt Sally. Okay. Whichever one works for you, you can go ahead and remember it that way. I remember it with the PEMDAS, but I always remember the other one too. The important thing when you're using these acronyms is that, even though M comes before D, you have to remember that they really go together. Okay, and that division and multiplication are treated in the same step, and you just go left to right. Same with addition and subtraction. So let's look at a couple of examples. So we have four operations here, right? We have the exponent. We have the so we have the exponent with the 5. We have the multiplication, which is the 5 squared times whatever's in the parentheses. We have the parentheses. We have the addition, and we have subtraction. So we have like 5 things going on. So always we should look at the parentheses first. So we do whatever's in the parentheses. Okay. So we do the 3 plus 4 to get 7. Now we have an exponent, multiplication, and subtraction. So from our acronym, the exponent comes first. So 5 squared is 25 times 7. Okay. Now we have multiplication and subtraction. So multiplication from our acronym comes before subtraction. So we do 25 times 7, which is what, 175, I believe, minus 7. And now we just have one thing left, which is the subtraction. Okay. So you get 168. You'll have lots of these in the homework, which goes up at the end of the week. Yeah, let's do another example next to it. Whoops. Sorry, I went too far off the screen here. So we have a bracket 5 parentheses 3 squared minus 8 close parentheses plus 2 close bracket divided by 7. So the brackets just serve as like another type of parentheses. We don't typically want to use parentheses more than once, so we'll use brackets instead sometimes. But it means the same thing as parentheses. So what happens when we have two parentheses? Well, so first of all, we know we're supposed to do parentheses first, right? If we're just looking at the whole thing, if we're choosing between the brackets and the 7, we choose the brackets. Now we have to zoom into the brackets and do what's in here. What do we do first in here? Well, we go back to our acronym and it says parentheses. So ultimately, it's going to lead us to the innermost parentheses to do first. Okay. So we should do the 3 squared minus 8. But now we have another question, exponent or subtraction? So we go over to our acronym here and it says exponent first. So the exponent is 3 squared, so we have 9. Okay. Now we still want to work on the innermost parentheses, so we should do what's next, which is the subtraction, and we get 1. Okay. So now we're still working inside this parentheses. We have multiplication and addition. So multiplication is going to come first. Of course, 5 times 1 is just 5, so there's nothing really to do in this step. Now we only have one thing left in the parentheses, which is addition. Okay, so we have 7 divided by 7. You don't really need the brackets anymore because you already did everything in them. So you can just write 7. And so the last thing we have is division. 7 divided by 7 gives us 1. Okay. So we want to work on the outermost parentheses down to the innermost parentheses. Okay. So there's lots of different examples we can do with these. I'm going to, like I said, give you some on the homework. I'd like to point out one more. Um, Actually, I'll save it for homework. So I think I'll just do these two. If you need more examples, please contact me. I'll send you a lot more if you'd like. And that's going to be it for this chapter. So we're going to just do a little bit of 2.2. We actually already did some of 2.2. The combined like terms thing was part of 2.2. I just thought it kind of fit better here. So we'll do that. We'll do the rest of 2.2 next time. And then we'll move on to 2.3, which is one of our most important chapters. So thank you for watching this. Let me know if you're having any questions. And I'll see you next week for the next one.